Hello. Am I audible?
Yes, sir.
Yeah. Oh, sorry. So we are going to study this topic today, hash functions, secure hash algorithm, actually, SHA. So I hope you know about the hash functions. What is the hash function? So basically, if you give the input to that function, it creates a hash value, right? So you use some function on X, and that function will create the hash value. Okay. Now there are plenty of algorithms which are available for hash, or plenty of functions are which are available for hash. Now the size of X data can be anything. So that means it can be a document, it can be a long file, it can be a simple number, it can be a simple small text. And then you produce a hash which is of fixed size. Okay, so whatever the size of the input is, it doesn't matter. This function has to produce the same size of the hash all the time. Okay, so basically, an hash function is a constant value for that particular X input, and you use this hash function to check the integrity. If you remember the CIA triad, what is CIA triad? Confidentiality, integrity, and authentication. Okay, so if you want to check whether the original X has been received at the end or at the receiver side, you check the hash value, or you calculate the hash value. And once you do that, once the hash value matches with the original message or the received message, then you have achieved the integrity. There is no change in the original message. So this hash function is used for integrity, checking the integrity. But there are few problems with the hash function. You have to check the collisions. What is a collision? That means what? Suppose there are two inputs, different inputs. If this function produces the same hash for both the inputs, then there is a collision. Okay, so your function should not be having any kind of conclusion. Okay, so you consider any two inputs at random. This should not happen. Okay, so that is the basic of hash function. Now we'll look at what is the secure hash algorithm. Okay, that is SHA. Now there are plenty of versions of SHA, SHA 1, 2, 3, and so on. Now, so what I'll do is I'll give you the basic structure, bird eye view of SHA1. Okay, so let us consider this as a SHA algorithm. It takes the input, message, there is some message. Okay, now every time this message length is different. Okay, if you are considering a 5 MB file, the size of this message is 5 MB. If you are just giving 2-digit number, then it is actually different size. So what happens is, for this SHA function, what you do is you divide this message into number of blocks, x1, x2, x3, and so on. Okay, and if and make this size as fixed. Let's say 512 bits. Okay. So in SHA, the input for SHA algorithm is 512 bits. And whatever the original message you have, you create the 512 bits blocks. Okay. Now, some of the blocks will not be of 512 bits because not every message can be divided in equal 512 bits. So what you have to do is you have to do a padding here. In case padding of zeros, in case there is a one block which is less than 512 bits. Okay, so that is the first step of SHA1. Right. Then it produces a hash, okay, of 160 bits. Usually the hash which you produce, it is of 160 bits, and in SHA, all the versions, SHA 1, 2, 3, this output is always 160 bit output. Okay, so actually the bird eye view says that message goes in SHA1 algorithm and it produces the hash. Okay, but I'm giving you a little bit more idea about how the message is getting divided and how this process will do. Now there are plenty of blocks here. First, you are putting the blocks one by one. Okay, and for the next block, what you do is if you remember the blockchaining mode, cipher blockchaining mode, you put the you do the operations on two inputs in each block. Okay, so what you do is the previous hash value will go back into the process, and once all the blocks are done, final output will be h of n. Okay, so this is what SHA does. Now, why it is secure? We have to look what is happening here. Okay, actually, this is called as a compression function. Why it is called as compression function? Because you are reducing 512 bits into 160 bit. Okay, so that's why it is also called as 512 bits. Now, if you remember the Feastal function structure, what it does is it has, now I'll give you a detailed idea of what SHA happens, whatever is happening here. Okay, now there are rounds. What happens is you have a round one, round zero, round two, round one, round two, and so on till round n. And for each one, you have a key schedule, right? So you provide a separate key for each round. Right. So this is what usually the Feastal structure is. Okay. Now let us try to modify this, how this is modified for SHA. Okay. Basically, SHA has 80 rounds. Okay, so value there are 80 rounds. So if you are starting with 0, it will have 79 rounds. 0 to 79. Okay. Now for all these 80 rounds, you'll have to provide these 80 keys. Okay. And what is the output of each round? It is actually a 160 bit. Okay. What is the input for each round? 512 bits. Okay. Now there is a problem here. Every time in each round, you'll have to do a compression. Okay. So to reduce this complexity, what change they have made in SHA is, instead of key schedule, we have a message schedule here. You don't provide a key, you provide a message for each round. Now, what is the message size here at each round? At a time, only one block is going into the 80 rounds. So the message size is 512 bits. Okay. Now these 512 bits, let's say you want to create many rounds here, many parts of this message, because 512 bits again is going into all the rounds. Okay, so at a time, each round will be considered as, the other input will be considered as 32 bit. Okay, so there are W0, W1, W2. These are the words. Okay, one word is of 32 bits. The message, the XI message, the part of that message, XI, is divided into 32-bit words. Okay, so there are these words has to be inputted for each round, and you have to create 79 such words. I'm sorry, 80 such words till W79, and you'll have to provide those as input to each round. Okay. Now, if you consider here as a 160 bit, each round takes 160 bit input and creates 160 bit output. Okay. Now what is happening here? How will you get this input 160 bit? If you have noticed that what is happening here, for each round, the next 160 bit is going into the next round. So what we are doing here, the previous rounds output, okay, previous all SHA rounds output is going into round 0 as an another input. So this is 160 bit one input. The second input is word, 32 bit input. Okay, so this is another, this is a bird eye view, and this is what you can say, another we are focusing into the algorithm here, SHA1 algorithm. We still have to focus into more, because we don't know what is happening in each round. Okay, we still have to find out that. But right now, have you got this concept of SHA? Any doubts here, guys? Just go through this page. If you have any queries, please let me know.
Sir,
Yeah.
I have one doubt.
Yeah.
So the rounds will be varying according to like how many key divisions they are like generated according to that, right?
How many keys?
I mean, like the W1, W0, W1. According to that, we'll have our rounds.
Right. No. W is just a what you can say input. One input. Round, whatever the contents of the round is again a difficult part that I still have to explain you what is happening with 32-bit word and 160-bit word. But what I'm want to do here is I want you to understand the basic idea of what SHA has, what SHA steps are there, basic steps. The round doesn't depend on each word. Actually, these are the 80 inputs which are coming from actual original message. Part of the message, sorry. I'll tell you how to create these W0 at the end. I'll also tell you what is happening in each round. Okay, because there are plenty of details are still missing in this algorithm. But as of now, if you have explained, if you have understood whatever I have explained. Okay, now there are 80 rounds in the SHA. What happens is you have to, the SHA 80 rounds are divided into 4 stages. Okay, so there are 4 stages. Each stage is of 20 rounds, and that's how you prepare 80 rounds. Okay, so each stage you have T1, T2, T3, and T4. Okay, so the each for each stage the rounds are completely different. So each stage, all these 20 rounds, let's say first 20 rounds is a stage 1. Okay, that means what? Round 0 to round 19. Then T2, stage 2 will have round 20 to round 39. T3, round 40 to 59. And round 60 to round 79. Okay, so these are the rounds which are divided into 4 stages. Okay, and we will see what are the different what is the different in each stage. Okay, so we'll consider each stage as different. I'll explain it on. Right. So now what is happening at each stage, that is the question. Next question, that is first question. The second question is what is happening in each round. Okay, now let us expand this round, what is happening in this round. Okay, basically what is the input you are giving to this round? It is 160-bit. Okay, we have to divide this 160-bit into 5 sections of 32-bit each. So 32-bit will be constituting 160. So let me draw a diagram here. Okay, so we'll name these blocks as A, B, C, D, E block. Okay, now each block is of 32-bit and total is of 160. Okay, 32 into 5. Now, if you remember the Feastal function or DS function, we have divided the message into left part and right part. Okay, so what happens is you work with the symmetric here. Now here there is no symmetry. Okay, there are 5 sections. Okay, so what happens here is in the Feastal function, what you do is you XOR this with some you apply some function on right hand part. Whatever the output is, you XOR it with left part, and then you switch it on the right part. So left part goes on the right part and right part goes on the left part. So this is what happens in Feastal function, basic DS algorithm. Okay. Now in SHA, similar method will be used, but with more complexity is increased in SHA1. Okay. Now in this encryption happens on left part. Okay, here encryption is happening on E part. So let me give you one operator here. This is the new operator. This is not XOR operator. This is XOR operator is this one. Okay. This is the new operator which takes the input. This is 32-bit. This is I'm sorry, not this one. It will get some other input. It will go in next 4 stages. Okay. Now this operator is modulo n operator. Okay, it is a very simple operator. What it does, it adds up 2 integers. Okay, let's say 32-bit integer is there. Okay, so what it does, it adds these 2 numbers. Let's say this is 3 modulo 3-bit operator. What it does, it adds these 2 numbers and ignores this carry bit. That means what? It takes 32 bits input and it produces a 32-bit output. So whenever you are adding 2 32 bits inputs, then it is not possible that always you'll get 32-bit output. Obviously, after addition, there will be some in some cases there will be some carry. Okay, so in case there is a carry, you have to ignore that carry, and that operation is a modulo n operator. Okay, it's a very simple thing. And this block, E block, is going into 4 different additions, modulo n addition. Okay. Now, for the first one, what is the input you are getting? Okay. So what happens is there is a one feastal function which takes three inputs. Okay, B, C, D, and B, C, and D are going into this feastal function, and the output will be again a 32-bit. Okay, and the output is going for the first modulo n operator. Okay, so these two things will be added, and then whatever the output is there, it will go into the next operator. Now, what is the second input for the second operator? Okay, what you have to do is you have to shift this block by shift left by 5 positions. Okay, and after shifting left, you have to rotate left, obviously. This is the rotate left by 5 positions, and whatever the after rotation, whatever the 32-bit you have got, you always remember everything is now 32 bits. Okay, that is the second input for the next round. Okay, not round, this is the one round operation. Next operator. Okay, now the output of this addition is going to the next one. Okay, now for the next one, what is happening is you are getting the actual, if you remember, these words also have to be considered in the rounds. Okay, W0, W1, and so on. So what happens is, can you tell me how many words you can prepare of 5 and 2 bits? Because the original message, original block is of 5 and 2 bits. Okay, and W0 is of 32 bit. How many such words you can prepare out of 5 and 2 bits? What's the answer?
16.
16 or okay. Okay, 16, right? Now, what you have to do is, you can say that you have to provide a WI for the next one, next operator. So this is a 32-bit again, this is 32-bit. Next operator takes these two inputs. Okay, and if we have seen there are some stages, T1, T2, T3, T4. Okay, so for first 20 rounds, okay, there is one constant. Okay, there is one constant that goes in the fourth operator, that is that we'll call it as KT. Okay, and T value depends on which round you are working on. Let us say this is round 0. Okay, in that case, it will be 0. T will be 1, so it will be K1. Okay, if the round number is R20 or R25, or it lies between these two, this stage, then the constant will be K2. Okay, I'll explain about this part a bit later, but right now you just understand that this is a constant which is getting into the fourth operator. Okay, now, yeah, and then the output of this has to be going for the next round. So this is the next round's block. Okay, that means next round has again 5 blocks: A, B, C, D, E. Okay, so this is the input for the round. This is the input for the round, and this is the output for the. Okay, so this E block is getting encrypted so well. Okay, the only thing is that you can't put the this output at the same location. If you remember what we are doing, we are in each round we are swapping these things, right? So if you are copying this as it is in at this location, what will happen is in the next round, because this round is getting repeated, only this part will be only this part is getting encrypted. So instead of that, what you are going to do is you are going to shift this E at this location. Okay, then D you are shifting at this location. So next time in the next round, is it not visible for you? Okay, so D is getting shifted, and in the next round, this block will be encrypted. This C is getting shifted at D location. This B is getting shifted at C location, and this A guy is not getting shifted as it is. What it does, what you have to do is you have to shift 30 bits left. Okay, and then transfer it to the next location. So what you're doing is in each round, we are actually encrypting one block. And for the next round, we are shifting each block one position right. Okay, so that each block gets encrypted in each round. Okay. And there are only shift operations working on block number A. Okay. Is there any doubt here in this step? This is the round, any round you can consider round I's view. This is what it is happening in each round. Any doubts? Uh, I think you are muted. Hello?
Sir, I said no doubts.
Sorry. Right. So now what is not known here is what is happening at Feastal function. Okay. Actually, I was expecting the question here, what is happening at this block and what are these, how these are prepared. I have given you the hint as only 16 words you can provide from 5 and 2 bits. Okay. And how many such words you have to provide? 80 words you have to provide. You have only 16 words. How to prepare these words? Okay, so these are the two questions that needs to be answered. Okay, and what is these KT? Okay, so let us check out that part. For different stages, T1, T2, T3, T4. Okay, there is some constant k, and there is some function. Okay, this feastal function is also different for different stages. Okay, so I don't know what is constant. It is of 32-bit. I can't remember them now. But what you can do is you can Google it. It will have some 32-bit data, some constant data. Okay. What I'll tell you is what is the feastal function, which is different for each stage. Okay. Feastal function is taking the how many inputs? See, there are 3 inputs, B, C, and D. Okay, so you have to work on these 3 blocks in the function, feastal function. So for stage 1, what happens is you have to work on these 3 inputs as B and D or B and C. So this is the feastal function. Simple OR and OR operator and AND operator. For stage 2, feastal function goes as B XOR C XOR D. I'm sorry, I should not have rounded C. So B XOR C XOR D. So that is the function, feastal function for stage 2. For stage 3, B and C, C and D, B and D, and you put OR operations. Okay, so that is the function, that is the operations for stage 3, and stage 4 is repeated here, B XOR C XOR D. Okay, so these are the functions that you have to perform in the feastal function on these 3 operators. Okay, now what is not known is how the message schedule works. Okay, KT, that is constant for each round, is different. You have to Google it for the values. If you have interest, you can check it out on the Google. Now, what is remaining in this SHA1 is key schedule. I'm sorry, message schedule. Okay, how the words are prepared and given to the each round. Now the problem with us is we have 512 bits. Okay, so with 512 bits we can prepare W0, W1, W2 and so on till W15, as there are only 16 words. Okay, now what we have to do is we have to prepare W0, W1 till W79, right? So for the first 16 rounds, all these are copied as it is. Okay, but for the next one, W16, you'll have to work on these words. Okay, now what happens is, let us consider as the new index as WJ. How will you calculate WJ? Okay, so WJ is calculated as WJ minus 16 XOR. So you take the first word, XOR it with some other, WJ minus 14. Okay, then you have to XOR with some other word, then you XOR with some other word, and then you prepare it and copy it to the 16. So these are the words as WJ minus 14, WJ minus 8, and WJ minus 3. Okay, so what you have to do is to create the new word, you have to work on 4 different earlier words. And what are the earlier words? J16, J15, J8, and J-3. Okay, you have to get the previous words and XOR them together to produce the new word. And as you move ahead, okay, these J value will keep changing, and you are producing those words for these rounds. Okay, so this is all about SHA algorithm. Secure hash algorithm. And it is so secure that whatever we have discussed is quite complex things. What I suggest you is we'll just have a quick review of what we have seen. So actual message gets divided into number of blocks. Each block is of 512 bits. It goes in SHA1, it produces 160 bit of hash. Okay. And for each round, the previous hash is used as a 2 inputs for the SHA. Okay. And after 80 rounds, you are producing actual hash. This is not actual M, this is hash of X1. Okay. And what is happening in the SHA1, as there are 80 rounds, round 0 to round 79. For each round, you're having message schedule. And for each round, there are 2 inputs. One is 160 bit of previous one, and other input is word taken from X1. Okay, we just have seen how the words are prepared. And for each round, the output is 160 bit. Okay. Yeah, and what is happening in each round is this one. If you have any doubts, we can discuss. And this is the message schedule algorithm. In feastal function, you have a key schedule algorithm. Here in SHA, you have a message schedule, because we are working on a hash function of message. Which keys are used here? These are the keys which are used here. So if you don't have any questions, we can